Good morning, everybody. My name is Javier Goicoechea. In case you don't know me, I'm from Madrid. And it's a real pleasure to introduce you Emmanuel Dartois from GISM3, Orsay, so close to Paris. He's a very good astronomer, but the important thing is that this is the kind of scientist that do laboratory astrophysics. Okay, so sometimes we can reproduce interstellar environments in the lab and learn about the fundamental processes in the lab. Okay, so he will tell you everything you need to know about dust grains in the ISM.
Thank you, Javier. Well, I won't tell you all.
Most.
In an hour and a half, but I will try to present you a kind of flavor of some interstellar grains. We've heard that they are an important component in the models. They are catalysts, as Serena was saying, but they have different natures, and I will try to go through several flavors during this talk, and I would like first to thank the organizer for this very nice venue before to start. So I also invite you to have a look at the very nice presentations made in the previous edition of this meeting from Karine Demick and Nathalie Izard, where you will have complementary or overlapping aspects of what I will be discussing today. And they are really nice, these lectures, so I really invite you to have a look at them. As an introduction, so we will look at some key ingredients to study the interstellar solid in the laboratory. I'm coming from the ISM community initially and moving more and more towards protoplanetary disk also, which incorporates what you have in the diffuse ISM of a galaxy, and mostly oriented toward the galactic sources where you can get sensitivity, resolution, but at the expense that you are looking at very specific objects, but still you can get a lot of information about the composition of dust that you will find in a way or another in other environments you are interested in galaxies. So I will look at the life cycle, the wavelengths of interest, talk about a bit about the budget and the energetic environment that can make this dust evolve, starting with silicates, and then carbon nanotropes. Maybe I'll go to the transition from the diffuse to dense ISM, the signature for ISM solids incorporation in the solar system, but maybe not. We'll see how it goes when we'll be there. So, of course, you have already seen this kind of cycles during this meeting. At the galactic scale, the dust life cycle we are exploring is looking at the different phases you have and the different exchange you have between the different phases in a galaxy, starting with, for example, the end of the life of stars injecting matter into the interstellar medium, then going to dense molecular clouds and stars. We have discussed a lot about dust. There have been not a lot of plots showing you the size distribution you expect for this dust grain, because this is an important aspect. If you look at the diffuse interstellar medium, typically you will have bare grains made of, we'll see, refractory solids with sizes between 0.5 to 300 nanometer typical, and with a power law size distribution, which means that all the processes requiring a surface are generally dominated by the small sizes, but the majority of the mass is in the large grains if you integrate these grains. And of course, when you enter into the dense part of molecular clouds, you can go to the stellar formation patterns, and in which you can go through different classes of objects where you can see the evolution of dust, and we will go back on this later. And of course, I won't have the time to touch this, but our own solar system is one realization of the evolution of all these processes, incorporating potentially what have been processed in the interstellar medium. And this is a place where you can get some samples you can bring back to the lab, whereas in the other cases, you're limited to remote observation. So it has advantages, but it also has been highly reprocessed. In terms of interstellar dust budgets, there have been many aspects already touched in the previous talks about the feedbacks. So the ingredients to produce dust, a large part of the dust is produced by stars, flows, and end-of-life ejectors. As shown in this old diagram here, you have the injection mass. There are more recent ones. I mean, you probably have your favorite one at the galactic scales. The supernova injection of dust, but also a lot of dust destruction. So the net effect of supernova is not always favorable in terms of the dust, but it injects more EVO elements. Something that is, for me, overlooked are the stellar feedback, not only in terms of energy, but also when you are coming into the process of the formation of a stellar and a system with a surrounding disk, you also reinject a lot of dust through all the loss of angular momentum and the rejection of dust into the interstellar medium that you have potentially reprocessed. So it's a new kind of dust that you can reinject in the medium of a galaxy, and it's also the case for all the PDR regions that have been discussed during the previous talks. At the interfaces, you can modify the dust and then re-inject it into the system, and we will see also some potential reformation directly in the diffuse medium at some point. So starting with the basics. So for some of you, some of this will be very obvious, for some not. So we already have heard about the depletion of the different elements. So if you look at the elements you are expected to see in the interstellar medium, you are generally dominated by oxygen, and the depletion of oxygen in the diffuse medium is about half of its abundance. If you look at the EVO elements like magnesium, silicon, sulfur, and iron, they are almost completely depleted from the gas phase rather rapidly. And so you can expect that combining this to this, you would get some minerals. And in fact, this is the reason why you see silicates. If some carbon is remaining and not used to do small molecules, then you can also incorporate it to form carbonaceous matter, especially if you have put a lot of oxygen in minerals. You need 3 to 4 oxygen atom per element here to get silicates. So you still have some carbon left to produce carbonaceous material. Of interest are the different wavelengths where you can characterize the composition of this dust. So it's always a trade-off between the wavelength accessibility and the spectral signatures, as would be something that could be interested in a round table. It's what is the observational bias that drives your science, because sometimes you would like to see everything, but you do not see everything. So how do you cope with that, and how it influences your own way of seeing the elements you put in your models? With respect to solids, I show here a typical spectrum of a silicate from the sub-millimeter to the visible, and you see the absorption part of the optical indexes. So basically here you have strong signatures in the infrared, then nothing, almost nothing in the visible, and again in the UV. Which means that if we had no observation in the infrared for many of these solids, we wouldn't know what are their composition. And so it's a very crucial element, this wavelength range. in addition to the other ranges, but this is really a crucial one. And these wavelengths of interest, when you're looking at specific objects in our galaxy, and during the stellar formation, you also have some observational biases depending on the evolutionary stage of what you are looking at. If you are really in the early class of objects, so really the start of a condensation, you generally are observing a black body at very low energy, and so you don't see much of this of the composition of the dust, and you start to see it at later stages in the evolution. Just an historical short slide about infrared astronomy. As you've seen, it's an important point for the determination of the composition of solids. For most of you, many of you were not born when IRAS was sent. More were born, but not necessarily already in science when the Infrared Space Observatory was sent. Then came Akari, Spitzer, and if you notice, all these infrared, mid-infrared and near-infrared telescopes have at sizes of about 60 to 70, 80 centimeters. So apart from Herschel, which was more at longer wavelengths with a larger mirror, then James Webb is a giant leap into the sensitivity and spatial resolution you can get. But still, you had some information from these various previous missions. Important also in what I will show you are the different energetic sources of evolution that drives the evolution of the gas, as we've seen a lot, but also the dust. Here is a non-exhaustive list of these sources, the photon sources. If you really want to make a difference, you need quite high energetic photons. So generally, typically in the vacuum ultraviolet, so very short wavelengths range. So you get evolution of the dust potentially from the ambient field, so the stellar field, the generic stellar field you have in a galaxy. Stellar, if you are in a configuration that you have a specific source close to the object you are looking at. Also, sometimes not well known is the cosmic ray induced secondary UV field that you get into the dense class. So if you get by extinction, you get rid of the external UV photons. At some point, the EV atoms, the atoms at high energy going and propagating through the cloud, we drive by interaction with hydrogen, and we've seen some of the equation in some previous talks. We drive the formation of local excitations of hydrogen leading to UV. So you still have UV even if you are extremely well shielded from outside. So the level is getting down, but you still have some. X-rays make also evolve things. Particle sources themselves, so the cosmic rays themselves, they can also interact directly going through the dust grains, in addition to producing secondary UV field. Potentially electrons, as well as all the other mechanisms we've heard about. So the thermal evolution of sources generally around stars, as well as temperature-induced or pressure-induced mechanism in the various kind of shocks you can find, the continuous one, the jump shocks, as well as all the shattering and collision in between grains that you can have in these regions that will make the dust evolve. If you want a very simplified picture of the kind of solids you will find in an interstellar medium, then this is a very basic schematic. You will find the so-called refractory solids on the left part, consisting of minerals, and we'll go on details just after. as well as a broad term carbonaceous matter, so containing carbon, but also all the other elements you can put into it, oxygen, nitrogen, etc. These are, as an abuse of language in astrophysics, called refractory solids. So refractory means non-volatile at room temperature here, but it's not refractory in the usual sense. As well as when you're entering into denser regions, the presence of ice mantles. So because you are at low temperature and sufficiently shielded, you start to accrete and to develop mantles on top of these dust grains. And they are called volatile solids because they can play a role in interfacing the gas phase to the solid phase, as they are both condensable and volatile. And ICs here is again an abuse of language. It means everything that you would have at room temperature gaseous and that you would condense at 10K. So everything except maybe H2 or helium. So inorganic dust, the so-called silicates. So so we will enter into a bit of very naive physicochemical structures of the important minerals you can find in your observations at galactic scales. So among the major ones that you can find are the so-called olivine and pyroxene components. So their names are in principle given when they are under a crystalline form. So often in astrophysics you find amorphous olivine. Amorphous olivine doesn't exist. It's olivine of the composition of crystalline olivine that is intended when you see this. Structurally, they are quite different. You see here that olivine has a tetrahedron of oxygen linked, and there are intermediate divalent cations at different position in the matrix. And the result of this is that for 2 divalent cations, you need 1 silicon atom and 4 oxygen atoms. In the case of pyroxene, which is another flavor of some of the minerals, you get again the same kind of formula, except that the some of the oxygen atoms are shared in the chain in the crystalline structure, and so you get something which requires only 3 oxygen atoms per silicon. So it has an influence. What you can form also is also depending on the elemental abundances you get, in addition to the physics related to these minerals. The silicate mineralogy is much more complex than these 2 ones. And of course, there are flavors even into these silicates. You can, if you go to the so-called magnesium pole of olivines, you would get Mg2SiO4, so called forsterite. You may have heard about it. If you would have only iron, it would be thiolite. So you do not often, you're not supposed to find this in space. So with that amount of iron. And for pyroxene, again, you have different poles, enstatite and hyperstene or ferrosilite. And you can also add other elements that are less abundant to form diopside and debagate. So you have a very large amount of potential silicates you can form and have, and they may influence the spectra you're observing. Again, in the same vein, you have here the olivine pyroxene group, amphibole group. So the structure and how they share this substructure lead you to the formation of very different kind of silicates. So you have an entire family that is much broader than what is generally used in some models. So now, if we look at the evolution of these silicates in their journey in our galaxy. starting from where they come from. So if you look at some of the progenitors of dust, I just mentioned at the beginning, so the stellar flows, and in particular the asymptotic giant branch stellar flows. You here have a kind of sketch of the different physical conditions you will get when you're looking at such a dust formation, dust and gas formation flow. And there are a few important points which will drive what kind of silicates you form and which form they will have, and the dust in general. So you can have quite high densities at some point in the dynamical atmosphere and the wind acceleration. So here you are at about 10 stellar radii, and then you get to the circumstellar envelope. And then at some point, you get to the ISM. So one important aspect is that in this regime, so you can place the bar slightly at different positions, but in this regime, you are at quite high density and pressures. And you are starting with very small seeds that you will nucleate. And you will have a nucleation chemistry. And depending on the conditions, we will see you can form very distinct kind of dusts. And once you have passed a given distance from the star, you will the density will decrease fast enough that you won't be able to have these dust particles and the atoms to meet efficiently again. And then you will start to enter into the evolution range of the dust you have produced. If you want, feel free, I forgot to say this, but feel free to ask questions and raise your hand and wave it widely if you want, and I try to answer. If we look at the stellar wind model, so as I said, if you have here a kind of cooling track, so here the pressure is in din per square centimeter. You have a kind of cooling track when the temperature is going down from the star and the pressure. And so for a given elemental composition in the wind, you will start to first, in general, you will be in a thermodynamical state to form, for example, here olivine. The condensation still can occur far from the equilibrium at about 1000 K and rather high pressures you can get in the lab, 10 to the minus 10 atmosphere. There is a critical phase when you're going from the seeds to the formation of the first dust particles, because you are in an unstable region in the nucleation where you need to make bigger particles than what the thermodynamics tells you. You are really at the point you are in an unstable equilibrium, and so you require a saturation. And of course, there is the competition between the characteristic formation and ejection timescale, as I was saying. At some point, you will freeze the reaction just because the kinetic is no longer efficient to form large dust grains. So I took all slides, but they are very young with respect to the age of the universe and still valid. I mean, you will find many eventually more recent papers, but there is a line drawn generally in the evolution of these envelopes depending on the carbon to oxygen ratio you have, which will vary from star to star, for envelope to envelope, but also will be time dependent. So in some stars, they will all start by being oxygen rich and then eventually go to carbon phase. And if you look at the temperature and the CO ratio, so if you are basically in a region you have an excess of oxygen, then the first solid that you can form are generally corundum, so aluminum oxide. And then if you lower the temperatures, you start to form the silicates. If you're on the other side, you will form seeds of small titanium carbide, small seeds of SiC at some point. So this is at equilibrium. And and so compounds dominated by carbon. But at some point, you will have consumed enough carbon in this decrease in temperature so that you go back to a mixed chemistry involving some silicates. So this is an important aspect of what you can inject in this from these envelopes. And here are examples from the past years of two different O-rich AGB stars, where in principle you have the same conditions, let's say from you're on that side. But in the first one, the wind is rather non-massive, so you have a low density ejection, quite rapid, and so you will form the aluminum oxide at the beginning, and then that's it. You will go in a region where the reactivity is frozen. Whereas in this one, which is much more massive, you start to see the silicates really formed in abundance and seen in extinction. So this was on specific stars. So the previous satellites already saw some kind of there is a lot of information was gained from spectroscopy. Even if you didn't have the sensitivity or James Webb, you still had some sufficient amount of stars with sufficient intensities to look at the mid infrared and up to the far infrared emissions of the dust around these objects. And thanks to this spectroscopic sensitivity, so around some stars, there have been seen a lot of very specific features, very sharp features that could be associated with the crystalline silicates ejected. And in some cases, the identification of the exact composition could be done. So here are just a few examples of this kind of silicate, very crystalline. The more crystalline you are, the easier it is to understand the composition, because you have very specific bands that you can compare to laboratory data. If you go then now from this start, and let's say you go to the interstellar medium and you look at the spectrum, looking at the galactic center. So you take a few stars with a circumstellar environment sufficient enough that you have a re-emission in infrared. You use this as a background. Let's assume that the background is as simple as the dashed line you see here, a black body in infrared. Then you see strong absorptions by looking at the entire diffuse medium between us and the galactic center. And then you see that some strong absorption around 10 micron, and you're used to these ones, and 20 micron, which are essentially SIO and bending and stretching modes of silicates, but now amorphous. So the question, to some extent, is what has happened, and we'll see that. So the silicates in the diffuse interstellar medium, if you look at the profile of the 10 micron feature, so you see something here, again, looking at galactic center sources, that is broadly an asymmetric Gaussian, and which is almost featureless, whereas what I showed before, that it should be injected by stars, are at least with a fraction and a significant fraction of crystalline silicates. So we will see what happened in between. So these were done looking at the galactic center. And these are much more recent observations, looking again at the interstellar medium in our galaxy, but with the possibility with James Webb to look at lines of sight not necessarily toward the galactic center and with lower column densities, so trying to have a more representative view of the diffuse ISM. But the scheme is the same. You see basically a broad an asymmetric feature that is basically dominated by amorphous silicates. So the evaluation of the fraction of amorphous silicates is like 99% amorphous, and you have the residual here. So as Javier said, I'm coming from the lab. And we try in the lab and many other people to produce analogs of the dust to study the composition and the relevant astrophysical environments. The lab determination of ISM silicates can be performed with different techniques and synthesized by different methods. So it includes sol gel methods, so where you will use here tetraethyl orthosilicates, so with the silicon and CO4 tetrahedron linked to organic moieties. And then if you simply put this into water, and you can hydrolyze the system, and then you will condense the SiO parts and get rid of the organic parts by producing ethanol, so you can drink what's remaining. And and you can add some magnesium, you can add some iron, and change the composition of your sol gel and explore the condensation of amorphous systems in that way. Other techniques use solid target ablation and recondensation. So in this case, you start with, for example, crystalline silicate, such as an olivine, and then you will shoot with a laser on this target, and then you will sublimate and vaporize the atoms making these silicates, and just in front recondense this onto a very cold surface. And so you will keep the composition, essentially the composition of your initial target, but you will recondense it from the atomic form at low temperature to see how it evolves. These studies are extremely important, and you will see, as I said, for example, in the DOMIC lecture, you can have more details of what I will show here in one slide. So from these sol gel experiments, you can record the spectra and get the optical constants, and in particular the famous mass absorption coefficients that many of you have used in some of your favorite models, to show that depending on the composition, it changes quite a lot. It's particularly important not only from when you're looking at the mid-infrared features that you compare to when you have very high spectroscopic resolution, but also because in the far infrared, the emissivity of this will change with respect to the different composition. And generally, in many cases, the masses of systems are estimated using the millimeter or sub-millimeter emissivity of the dust you put into the system. So you can get factors of 2 or 3 in the total mass you estimate, depending on what you assume. And this is something very important. Also very important is the fact that, especially in the far infrared and millimeter, the K constant of the optical constants can change with the temperature and can change quite radically. So depending on the temperature at which your dust is, you will also have a mismatch in between the mass estimate you make and what you have set as the composition if you use, for example, room temperature optical constants. So these laboratory data are very important to implement and to test into complex models. The ISM composition of these silicates, minerals, and in general, and organic matter can also be probed by using X-rays. We have heard this at the roundtable and before. It's not extremely well developed too much because of the difficulty and the lack of, to some extent, observatories with very high spatial and signal-to-noise resolution. But you can get this from the lab, so you will excite with an X-ray a solid, and you will excite an electron from the very core electrons, so that you will kick out. And so you will both get a spectrum in absorption when you're doing this, of the absorption here at the K edge. And you will also in the lab get, because this all you've created will be fed by electrons from the other levels coming back. You will have the emission of an X-ray photons that you can record. So here it's an example applied in the lab to extraterrestrial material. So here we are at the edge of the carbon atom energies. So an internal electron of a carbon atom. And you see that the position of the absorption will strongly depend on how this carbon atom is linked to the next elements. And so if you analyze these different substructure here, you can get an information on the kind of bonds you have in the system. And if you can image this, so this is a micrometeorite focus ion beam cross sections. You can even determine the composition of different composition in your system. This can be applied to observations by looking at X-ray sources. And to do so, you still need to perform all the experiments that I showed you just before. So by using standards of the different composition you expect to have in space, and then by comparing here at the magnesium KH, the silicon KH absorption along different lines of sight, then you can try to make a spectral decomposition of the composition you get along this line of sight. Here, these spectra were much more well-defined using amorphous olivine and a slight amount of carbon crystalline olivine. More recent observations along different lines of sight looking at other edges, the iron and oxygen electrons, internal electrons, led to different analysis. You have here the different line of sight observed, and here the different components used in the decomposition, and showing that mostly in that case you are dealing with Mg magnesium-rich amorphous pyroxene for most of the sources. Some of the dust in the column density could be in metallic form also. And another important aspect, there is no strong evidence for iron oxides such as hematites or iron sulfide that you find currently in meteorites. So what happens to these silicates? So they are when they are injected, as we've seen, they are injected with a fraction of crystalline composition. Then when you look at the diffuse medium, you see them amorphous. And then when you go to disks and later stages, you see them again silicate. So there are some evolutionary tracks. Why are they amorphous? So we will see this. There are many possibilities, among them reprocessing that change the structure. So either you volatilize everything and you recondense it out. These have been discussed in some papers, such as the Zubowska papers, where you would, in the low density part of the ISM, get to a point that you put back again a lot of silicon and oxygen in the gas phase, and then you recondense it. This is something that is extremely challenging from the kinetic point of view, because you are at very low densities. So the probability to recombine things at such low densities requires to really tune the parameters very efficiently. So you have to have ion chemistry to increase the cross sections of the encounters. So it's something that is still can be debated. Another way that maybe simpler and that is present in this environment are the influence of cosmic rays. So particles accelerated at rather high energy. So typically of mega electron volts to hundreds of mega electron volts, and crossing all the galaxy. And if they go through a silicate, they can kind of anneal the system and produce an amorphous phase. This energy deposition of cosmic rays, so cosmic rays are all the elements you have in the periodic table, from hydrogen to heavy element, but the most important ones are between hydrogen and nickel. And at these high energies, this is the energy deposition you get in a solid as a function of the energy of this system. You can put a lot of energy into deposit a lot of energy in a grain. And protons are the most abundant elements in cosmic rays, but the stopping power, the energy you deposit, scales as the square of the z of the element. So even if iron is less abundant, it can also have an impact, or heavier element can have an impact on what, depending on which process you are looking at, and can make a lot of damage into the solids. Experimentally, this has been demonstrated that, in fact, if you start with a crystalline silicate and you irradiate it, here with something that is rather low energy, helium plus, but still in the electronic regime of the interaction, starting from unstatite, you see that after some times of irradiation, you get something initially with a lot of structure, as would be crystalline silicate ejected, and then you lose the structure and you get something amorphous that resembles what you can have in space. There have been other experiments on other crystalline silicates and different energies, and to make a long story short, with 0.1 to 5 GeV cosmic rays, you can amorphize crystalline silicate in the diffuse medium within a few 10 of a million years. So it's an easy explanation for the fact that you are seeing them as fully amorphous in the diffuse medium. In any case, there are also these experiments I was mentioning about the recondensation of atomic phase directly at low temperature. These experiments performed by Gaël Rouillet, for example, showed that if you condense atoms at low temperature and you make them migrate, you can form some silicates and amorphous silicates. But the question from the point of view of the abundances in interstellar medium is that if you put everything back into the gas phase as atomic form, then you have a higher probability to have an encounter with a carbon atom than with a silicon atom. And so the question is, will you form only silicates, or will you form other forms that we don't necessarily see, such as silicon carbide? And it really depends on what kind of specific chemistry, and if you can separate the phases to be able to have this as an explanation for the amorphous silicates, in addition to the fact that you need the re-encounters of these atoms in low density phase. So if we now go to the dense molecular cloud, silicates are still present. Here are a few spectra of background stars behind a molecular cloud. Here around a protostar. You still see some silicates, just to mention them, and they are still amorphous at this stage. So they haven't evolved too much at this stage. Still, if you look at the evolution of the silicates in dense cloud at high extinction, here you have the depths of the silicate feature at 9.7 micron as a function of the K magnitude, so the extinction in the K band. So you start at low, so it's about a factor of 10 if you want the visual extinction as a proxy. So here you have at a visual extinction of about 10. You have something that is proportional at the beginning and corresponding roughly to what you see in the diffuse medium. But then when you are starting to enter into very dense part of clouds, you start to see a deviation, and generally you get a tau 9.7 that is slightly lower than what you would expect from the correlation, which in fact can be explained by the fact that you have a moderate increase of the grains when you're entering into, so you're changing the size distribution, so you're changing the ratio between the K magnitudes, the extinction in the K band and the silicates. It's not necessarily the silicates that are changing too much, but you are affecting the extinction curve you're using as a proxy to get the abundance. The silicates at the highest extinction, almost highest background star observed so far from a program led by Melissa McClure. You still have some silicates, but now they are not easy to see because you are dominated by the formation of the ice mantles on top of it. But still they are there, and they seem to be still amorphous in that phase. And other signatures from the ice you see here are subtle, and I won't go into too much details, but they are extremely deformed. And you are seeing, in fact, the evolution of the dust grains and the sizes that are increasing and which are responsible for these deformations. So you have this evolution of the lowering of the 209, but you have also other proxies telling you that the size distribution are changing. So these have been in model, and in that case, you're no longer in the case of core to mantle situation because you have all these dust grains acquiring mantles earlier that are now clustering, and so you get something that is much more heterogeneous than in the previous stages. We need to process this, and again, I will advocate for the lab experiments. So to be able to reproduce this observation and understand this change in the size distribution of dust, we need to get proper optical constants here from the ICs to add to these refractory mantles to model the shape and grain effects and compare them to the observations. And the grain growth is important when you're getting to these dense regions because they will impact not only the band profiles, but we've seen that as they are catalysts, they will potentially affect the available surface for astrochemistry. So you might change the consequence in your network when you're looking at this evolution. And so it will also affect the gas phase. If you look later in the circumstellar disk, then you start to see again some so later stages. It's very difficult to get to catch the intermediate stages. You get again spectra showing the presence of crystalline silicates. So we are looping back to some dust grains that are now evolving because of the processing of the sources and the stellar feedback to some extent. These are older observations, and these are very recent ones made with James Webb, where you again see some very nice crystalline features that allows to get an insight into the composition of these silicates. So spectroscopy and lab observations are very important to constrain and to know what kind of dust you are dealing with. Again, these are galactic observations, so they give you a flavor, but at some point in many of your dust in galaxies, you will have this kind of flavor potentially. So that's nice to be aware of what's happening even for specific sources. If you look at silicate in disks, if you look at the crystalline fraction, as I said, these are the easiest one to compare to lab data because you have very specific features. In some cases, when they are crystalline, the far infrared features, which are linked to the network linking this magnesium or iron divalent cations that are inside, depending on the relative proportion of magnesium to iron you get into these crystalline silicates, you will get some features that will appear at different spectral positions. And so you have a proxy for getting the fraction of magnesium to iron you get into the silicates. And in some cases, you can get this. This was the case for a few sources, and basically using Herschel, it was possible to show that in many of the disks observed, in fact, you were almost always dominated by a magnesium-rich silicate. So it doesn't mean that you don't have iron, but if you have iron, it might be in another phase if it's in the solid form. So basically, this is what is shown here. You replace iron by magnesium and you see a shift. And here you have the magnesium content as a function of the position. That is what's compared to spectra. And basically, the iron fraction was always almost compatible with no iron at all in these silicates, except for AB Origa, where it was 1%, 2%. So basically, you end up in these situations with grains that are iron poor, and you need a low fraction of iron into these silicates. Another aspect of the spectra you can exploit in the observation is the fact that when the size distribution is changing, it has an influence on the spectra. So here you have, I won't go into very details. I'm running out of time already. But if you look at this sequence here, you see, in fact, you imagine that you have the same composition of the grain. Then going from top to bottom, you have the SIO stretching mode features in emission that is going from Gaussian shape to flat top shape. And this is a direct effect due to the fact that the grain is growing and becoming of a significant size with respect to the wavelengths, and so you are affecting the band shape. So this might be an indication of a change in your size distribution that has to be taken into account. Of course, the difficulty of that is that you not only have shape effects, but you also have mineralogy effects. So in general, you combine amorphous silicates with if you don't have the very high resolution spectra in terms of spectral but also spatial information, you will mix amorphous and crystalline and size in the resulting spectrum. So it makes the thing quite complex sometimes. These again are just to show you flavors of very nice recent James Webb observations of this kind of spectral decomposition around disks, where you have here the derived composition for the object in terms of forsterite and statite and the grain sizes. So you have a combination of grain size and chemical composition needed to explain the diversity and the spectra you're observing. I will go quick on this. So you can still do also some ground-based observation of this if you're looking at very high resolution in disk. I won't go too much into detail, but of course, this reprocessing occurs close to the star, can be eventually rejected by the flows or the jet, or being incorporated in the future of the circumstellar disk, and you need very high resolution to go there. So I like the idea of the interferometer in space. And I agree with Jérôme, we need many telescopes to get the sensitivity and the spatial resolution. But from the ground, you can, in some of the atmospheric window, you can do this kind of studies to look at the chemical gradient in the composition in disks. But you could do the same, for example, in some starburst galaxies or in some AGN galaxies where you can see some crystalline features of silicates sometimes in absorption. So it's very important to get all this information at high resolution, and interferometers such as Matisse are very essential for that. So just a few glimpses. You can have a look at the papers after. I won't go into the silicate mineralogy using interferometry to get the information on the region very close to the star where you make most of the evolution of this dust structure and composition. So maybe I can make a very quick stop if you have questions here, or we do it at the end before I go to carbonaceous dust. And I will go fast. Yes. Patrice.
Yeah, just to make sure to understand, when you replace magnesium in the lattice, where is the iron going? It's still in the lattice.
First, we don't know what is the amount of iron you have initially. So we don't have access to it. But if you have iron, from the spectroscopic point of view, I can only tell you that it's not in this phase. It's not in the silicate phase. But it could be in metallic form, for example.
As an inclusion.
Yes. If it's in a metallic form, it won't affect what you see in this spectra. It will affect the continuum, and it will affect other parts of the optical constants, but not specifically these bands. So by replacing, I didn't intend it to mean physically replacing. It was just a sketch. So it's just a formal composition. Yeah.
More questions? No?
If not, I'm continue because I'm late. So carbonaceous dust, which is also a very important aspect of dust. I will try to go fast on this. So in terms of main carbonaceous solids observed in the interstellar medium in a nutshell, you can take a picture of that. So from the spectroscopic point of view and the lab comparison, diamonds have been identified in space, fullerenes since a few years. AIB, so I prefer the term aromatic infrared bands than pHs, because for a chemist, a pH is really like this and nothing else. And what we are sure of when we are looking at the emission bands is that there are aromatic infrared bands, because we are seeing vibrations of a polyaromatic system. And we'll see that truly pHs have been recently detected also in the millimeter. Often overlooked also are amorphous carbon and hydrogen amorphous carbon dust analogs, which are also important. Not a lot of graphite, even if they are used a lot in many models. They are not really spectroscopic evidence that we are having graphite, even if you find some in some pre-solar grains. It's not really a very strong component, but in some models it can be used to add opacities. And also the evolution of organic matter upon all these energetic processes I was telling. So the evolution of these ice mantles upon all the energetic processes can lead to the formation of macromolecular reticulated systems, so-called residues, that are much more stable than the precursors and can be maintained on the screen at higher temperatures. So in a nutshell, nanodiamonds are observed thanks to their hydrogenated fraction. So you are looking at the CH switching mode around big AB stars here compared to lab observations. So the first detection was done by Olivier Guillois in 1999. And have been compared to many to lab experiments. There have been several approaches from the lab point of view, looking at the top-down approach of the formation of this. So you take nanodiamonds and you decrease the size and you try to look at the spectra. And the bottom-up approach, looking at molecules and trying to increase the diamondoid molecules and trying to increase the size of this molecule to reproduce the spectra and calculations. And so typically the ratio of the bands you observe from the calculation and this would tell you that you have around 130 carbon atoms for these in these observations. These ones are, I won't enter into details, but this one we're advocating for very high sizes, but in fact you have a competition in between the production mode and the structure you get. So it's not as obvious as it might seem. Observationally, they are observed close to the stars, much more closer than pHs. There are 3 exemplary sources when you see it, so it's very bright detection. Laboratory comparison is very nice, but in fact you only have really 3 sources up to now where you really see the very sharp features. And it has been searched for because it was always around big AB. So there have been surveys of many big AB stars and was not observed in other sources so far. So it's an important from the spectroscopy point of view, but from the budget point of view, it might not be the major ones. And we'll see later with the sensitivity of GISM3 if we get some more information about that. Fullerenes, I don't know if you have heard about Fullerenes detections. Fullerenes have been searched for during a long time also. So these are the so-called football cages, so purely carbon, and it's really the shape of a soccer game, a soccer game ball. It has been spectroscopically done in matrices quite early, but there were mismatches and with the observation in space, and recently some action spectroscopy specific experiments were able to measure C60 plus at low temperature in the gas phase and compare this to diffuse infrared bands, so in the near infrared start of the visible, with a very good match of what is observed. And also showing that several bands were observed and that they correlate quite nicely when you correlate them in different line of sights. And so this identification is quite secure. It has been observed also in the infrareds because this molecule has many specific peculiarities that make it the easiest to detect among its family. So it's extremely symmetric. And so the number of vibrational modes you have is reduced, active vibrational modes. So you have only 4 modes active. And so it means that when you put the energy into the system, the re-emission will go through these 4 modes. So you will get a high contrast. So it's easier to detect. If you break the symmetry with 1 or 2 or 3 hydrogen atoms, you already lower the detectivity just because you are opening many ways of different vibration. But still, it has been observed in many sources, protoplanetary nebula, resolved in reflection nebula, which is also an important thing you can find in the diffuse ISM of galaxies. In principle, the percentage of the cosmic carbon when we are dealing with abundance you need to reproduce what is observed is not that huge. It's only a small fraction of carbon in total. But it's extremely important from the point of view of chemistry because making such a big system in space means you have very specific routes that are not necessarily still understood. And so sometimes even a small amount of a given system is extremely important just to constrain the environment. And so, well, it's more and more observed everywhere. So in the diffuse medium as C60 in the infrared and C60 plus in the visible. So it's something that is quite widespread if we want to compare to the nanodiamonds I was discussing. Of course, aromatic infrared bands. I guess that you are very interested in these ones because you observe it everywhere in every galaxy. Anytime you have some UV photons and a bit of density and interface, you get some AIBs, so astro pHs. What is maybe interesting here is when you look at galactic sources and you look at the various kinds of aromatic infrared bands you can observe, they have been classified in different classes. Initially ABC, depending on their spectral behavior. So you have here the CH stretching mode, the CC mode, at 6.2 micron. You have internal modes at 7.5 to 9 micron, and the CH out of plane modes. Generally, in terms of number of sources you find in a galaxy, you will be dominated in terms of class A. So these, which are really let's say, the most aromatic one you would expect. class B, and then class C and D. Class C and D can also be accompanied by the emission of aliphatic CH stitched to the structure, and they are often seen in the envelope close to the star. So the most, let's say, free-flying isolated are the class A. Class C and D, you're entering into sometimes in the thermal emission in some sources. Recently, pHs have been discussed a lot as pHs from the COMIS during many years, and recently, thanks to very sensitive surveys, both in Spain and in the US, some real pHs have been observed. They have been observed as generally as cyano pHs because in fact what you do is that these are less symmetrical, and you kind of attach an antenna to your system, and so you get a dipole moment that is extremely high, and so you detect it much more easily. So you will much more easily detect this than its the pure pH counterpart. And it has gone now up to Coronin and maybe even higher than this. And the column densities, it has been detected in the torus molecular cloud. And the column density you get are of the order of 10 to the 12 to 10 to the 13 per square centimeter, which is quite high for such a system, but still 10 to the minus 9 with respect to the column density you are probing. So they are really proof to be present. Now it's important to get some resolution to get where they are along the line of sight more precisely, but these are very tough detections, so it's really nice that we also have. And it's also something important for the astrochemistry, because if you look at the column density as a function of number of carbon atoms, it's rather flat. And it's not what you expect if you are making molecules by just the addition of atoms. You should expect a decrease in abundance with respect to the number of carbon atoms. So this is very young, so it will evolve in the coming years. So these pHs are also observed in what might interest you a lot are in photon-dominated regions, which are everywhere in a galaxy. Here, these are Orion bar observations from the PDRs for all early science program led by Olivier Bernet, Els Peters, and Emilia Barr. And thanks to the James Webb sensitivity, there is an incredible description of the profile of the AIBs you see in such a PDR. So this one is not very typical of a PDR in a galaxy because you have a 10 to the 4 luminosity star next to this bar, but there is a start of a study of all the substructure you get into this AIB emission that will help us in understanding what are the structure behind this. And there are, because of this exquisite spatial resolution and sensitivity, there are start of analysis that resemble the ones that we were discussing in the first week. Still in this, it's still in its infancy in the sense that here are PCA decompositions trying to look at the evolution of and the relation of different substructure in this emission, but this will probably will be boosted in the coming years. There are also studies of complemented by gas phase and looking at the evolution of some features of the dust, the aliphatic to aromatic CH ratio as a function of the penetration into the PDRs and the fronts. So Javier may discuss this this afternoon. I don't know, but you can ask him. And so you also see the evolution of the kind of dust as a function of the penetration, and so try to see what you should put in your models to see the evolution of this dust. From the lab point of view, if you look at the spectral features of the class C and D, they are quite well reproduced in the lab here with premix low pressure flame experiments combined to spectroscopy and some laboratory polyaromatic soot analog spectra. You have here what you expect in terms of number of aromatic CH over aliphatic as a function of the position of some specific bands. And you have here what you can reproduce in the lab. And so you see that at least for the class B and C, the 6.2 micron position as a function of the 7.7 micron band position allows you to know that in the lab you can produce analogs that are quite close to the so-called class C and class B in these AIBs. You can use other techniques. These are mechanochemical techniques used to produce also some polyaromatic systems by putting basically a lot of energy and not at equilibrium locally onto initially very graphitic or nanotubes or fullerene systems. And in the presence of hydrogen, you create a lot of defects in the system, and you can reproduce the observation of these class C and D structures. And here you have the transmission electron microscope images of the deformed structure you get. So some people look at this and say it looks like a fake suit, but it's again, it's something that we can produce in the lab, not necessarily with the same kind of size as you have in space, but internally the structure are close enough to what you observe in infrared. And the advantage of having the lab experiment is that you can compare some features so the CC with respect to the CH deformation. And make correlation plots of some samples produced in the lab and compare this to some sources. Some of them are galactic sources and some are extragalactic sources. So you have a good correlation here, and you can get from independent measurements the amount of hydrogen over carbon you get into the system that would cope with what is observed. And in fact, you realize that you don't need such a high percentage of hydrogen to get the features you are using here. It's only a few percent, so you're in a very reducing environment. But in fact, the backbone structure does not necessarily need to be extremely hydrogenated to produce what you are observing. These sources, which are AGNs or C-nitrogen, are dominated by hydrogen amorphous carbon absorptions, which we'll be going to. Amorphous carbon are also an important part of what is ejected from stellar environments, but also, as I was saying, quite difficult to observe because basically you see it very efficiently when it's close to its source of ejection, because you excite the amorphous carbon dust grains with sufficient energy to see a black body emission, which is for this kind of system almost a featureless black body emission. So you see it easily when you are close to a carbon star ejecting such matter. It becomes, of course, much more difficult when you're in the diffuse medium because you have no longer strong spectral signature apart from the UV part that will contribute to understand the presence of this. But they are quite really nice, and you see here recent observations of carbon-rich progenitors. And the sequence of ejection due to the activity of the star in terms of shells and the time evolution of these shells, as well as the spectra with James Webb. But this is also a component that is present in the carbonaceous dust you have in a galaxy. And later on, it can be hydrogenated or modified, but it's a fraction that is injected also and less easy to observe. Hydrogen amorphous carbon, as I was saying, is also an important component. So historically, it has been observed quite some time ago because some of the absorption at 3.4 micron are falling in a ground-based window. And basically, we are seeing at that stage the CH stretching mode of CH2 and CH3 in absorption, looking at sources along the galactic line of sight. There have been proposals of different structures which evolve with time and evolves in one way and then one way back. More or less aromatic. I tend to favor this structure rather than this one based on the spectra we have now, including the mid-infrared. These are the latest James Webb observations for lower column density lines of sight, trying to look at this amorphous fraction. I must say, I'm not fully convinced by the CH aromatic feature that appears here in the deconvolution, but this one is here, and so there are some discussion about the relative structure behind this. But this is an important component, and it's a low contrast one, in the sense that you need quite some column density to be able to probe it, because the intrinsic strains, absorption strains of the features are quite low. Whereas for PHs, if you have a few UV photons, you will excite immediately in emission, and you will be dominated by the emission. So this is also something we discussed when we were eating, that in many cases in starburst galaxies, you are completely blind. I mean, you are to some of the components I'm discussing here, just because you are having a lighthouse just in front of you and trying to look behind, and so it's important to have a diversity of ISM of galaxies probed to be able to understand what is the composition. But then you are biased by the kind of galaxies you are looking at, but I mean, there is no other way to do it. In the lab, you can produce this kind of hydrogen amorphous carbons. You have here a comparison between lab spectra of this kind of dust produced and the spectrum of the ISM or the circumstellar AGN dust of a galaxy at rather low redshift, but high enough so that we can see that there is no aromatic CH in this line of sight. So we are seeing something that is extremely favoring this kind of structure rather than the previous one I was showing. But these are school cases, as I was saying. So you have a few lines of sight where you are in a favorable orientation and stage of evolution of given galaxies, so that you can see it. But this is probably there also in the others, but very difficult to observe. These are extragalactic sources. So you have some, to prove what I'm saying, you have here some galactic sources, VLT observations of the CH features, and here a few cases of bright enough galaxies, famous NGC 1068 and 71, 72. So bright galaxies where you can see this. But with Spitzer, we had analyzed a lot more, also looking at the mid-infrared absorption, and we found something like 40 or 50 galaxies where you see these features. So looking at the features at 6.8 and 7.2 micron. And these again are some recent observations with James Webb of the presence of these in the diffuse ISM. To make a long story short and to end, I mentioned also the fact that, and I won't show more than one slide, and you can ask to some people in the room who knows that, I don't know, Patrice, for example, about some of what you can get if you irradiate ice mantles and make these condensed phases evolve under all these energetic processes I was discussing before, and you can make some so-called, so this is lab residues, starting from the precursors that you observe in the dense phases and just making them evolve under harsh UV or cosmic ray evolution. And this is also something that might be incorporated later or re-injected into diffuse ISM if you have some stellar feedback, chemical stellar feedback. So if I again make a kind of crude summary of the ISM carbonaceous solids ingredients, I tried to show you the signatures both from the observation and from the lab point of view. And now talking about budget. So nanodiamonds it's very nice. And from the spectroscopic point of view, it's really something exceptional. There are still some studies to know what is the fate of this under energetic processing. But the identification has been done firmly only in a few sources. Fullerenes, mainly C60, C60 plus, and in a few instances C60, C70 are an important component because they are quite now seen widespread, looking at the diffuse interstellar bands in the diffuse medium of our galaxy. In terms of budget, it's a low amount of carbon. In terms of chemistry, it's something important. AIB, pHs, class A to C. In many of the galactic models you're using, you need something depending on which flavor you're putting. I don't know, 5, 10, 15% of carbon locked into these. So this is an important component in terms of budget. Don't overlook the other components that you will probably need also, which are hydrogenated amorphous carbons, which are not seen in emission, they are seen in absorption. They are probably of slightly higher sizes and not necessarily a lot of emissive or being destroyed, but they are also present and they will probably contribute to the UV extinction you see in these line of sights. Plus the organic matter that I just mentioned in one slide. Well, so these are the big questions for another day. What are the observational biases that I mentioned behind this, and where are their location along the line of sight are something very important. Even at galactic scale, sometimes the notion of diffuse medium and where are these solids is not that obvious, and we are discussing it. And what is the microphysics evolution, and do we have really a transfer of this one toward this space, or are they really evolving separately is something important, and so are they mixed? Now, as I'm running a lot of time, I will go through many additional laboratory astrophysics experimental simulations of the processes involving solids. We need to know if what we are seeing is stable or not with respect to what you expect to have in space. So we need to do experiments to have an idea of the cross section of many processes. I mentioned already all these potential sources of evolution. An important aspect, which is of interest probably for most of you in galactic science and extragalactic science, are the passage from the diffuse to the dense medium. So all these interfaces, which are probably acting with a strong active chemistry, in particular because you are entering into a regime where the H to H2 transition occurs, but the UV field still is present to some extent. So it depends on how these PDRs are compressed. We've seen different situations. And this can drive chemical change, so re-put things on the gas phase and modify the solids, and then recondense it out because you have sufficient high densities to get this. Just to mention, so the evolution of the dust has an influence on the production of. Oops, faster. On the production of small and not small species at the interfaces, just to mention again photodissociation region and the kind of species that you might have from the destruction of dust grain, and especially the dynamics is something very important. What is the advection time of the processes when you are evolving the dense phase and the galactic medium is something very important. Are you having an influence of the top-down chemistry, breaking these largest grains and injecting moieties or ladders that you can climb to get to an evolution of your astrochemical models? We can do this experimentally again. As I'm running out of time, I will just show you. Now it's just movie time. We can produce these analogs that we know from the spectroscopy. We are not too far in terms of kind of analogs produced, and then torture them with whatever irradiation field we can produce in the lab, mimicking what you have in space, and looking at the byproducts. And the products you inject in the gas phase and their efficiencies, and then inject this into PDR models to see if you have an advection of a front, how you change the chemistry at the interface. So of course, if you're destroying the species, you need to have an advection front that is with a high speed enough so that you replenish your system regularly with the injection of new dust grains. But this kind of works. I will skip this. We can look at cosmic ray environments simulated also on large accelerators, such as the one you have in France, in Ganil, in Caen, or for example, in Darmstadt, in Germany, GSI. So you simulate cosmic rays and you see what it gives if you irradiate your system. Again, you produce, you destroy your grains and produce something that you inject and release in the gas phase, and you can feed the ladder. You can see the destruction timescales, which is what we have in hands-on, that we need to find the factor we have in our in this hands-on. And you can estimate the destruction rates, which are important to know if what you are seeing should be there or shouldn't be there, or do you need to reproduce these dust grains regularly, or are they resilient to the exposition of cosmic rays? And in some cases, if you're starting with AIB analogs, soot analogs, and you irradiate them with high energy ion beams mimicking cosmic rays, you can in fact eject species with a very high mass in the gas phase again. So the top-down chemistry can be active. Now it's important to do this experiment to try to have a kind of absolute cross-section that you can later give to modelers to see if it's feasible, or if it's a meaning, if it has a meaning or not. This is an example of one of the experiments we made, where you can see that in some cases you can even eject a species with 60 to hundreds of atoms, not in huge quantities, but still you have a mechanism where you can produce these species by impact with a cosmic ray. Photodesorption, the influence of UV photons, you can have a look also experimentally. Again, it's movie time. You can do the same for cosmic ray sputtering and put this into models. Moving very fast now. And look at the relative importance of all these mechanisms you measure in the lab as a function of depth in a region from the diffuse to dense, and this will have to be applied at the galactic scale in some of your models, and you can have a look at this if you want more details, and again do this also with very large species. Look at shock processing also experimentally, by exposing, for example, C60 and looking at to a shock wave simulated in the lab, and looking at the products you get in that case. And I guess I will end there because I'm lacking of time, and I don't know why it's not staying in this. So the lab experiments for gas grain detection, interaction, and energetic processes are very important. You need this lab data to make first the identification by comparing the spectroscopies of analogs and or species that are really the one you have in space. And from the VUV to the millimeter, it's very important to feed all your models. You can also explore the low temperature gas phase reactivity to see the chemical diversity, the famous catalyst effect of the dust grains. Look at the excitation and collision and UV pumping. Maybe Javier will talk about this. Surface reactions, you also have to measure it in the lab before to put it into the models, which are extremely highly demanding experiments. Look at the effect of cosmic ray, VUV, radical recombination, and also look at the evolution of all the spectral profile. I like spectroscopy and high resolution spectroscopy because we get a lot of information on these band profiles on the physical and chemical phase of solids, and look at also the thermal evolution can contribute to the chemical diversity. And I'm almost on time, but quite speedy. So thank you, and I'm waiting for your questions.
All right, so thank you very much for this very complete review of the field. Is there any question to Emmanuel? Yes,
So it was a very interesting talk. I'm not very familiar with experiments, but you touched on it a bit. We talked so much about what we need in the future for observations or simulations or data processing. What do you think should be or will be the next big step for not simulations, experiments?
In experiments, the most difficult thing to produce in the lab are solids, free flying, that you can hold a sufficient time to make it react with anything you want, atoms or energetic events. So this is something that is very important and challenging for the solid dust aspects. So that might be developments in that direction are extremely important, but you still need the classical spectroscopies and the knowledge from experimentalists. We were discussing this morning, so that's something a very important aspect to push the world politics, that we should have also instrumentalists and experimentalists in addition to modelers and statisticians. We need the whole complete set. But yes, maybe for the solid phase, yes, this being able to manipulate long time enough free-flying small particles, size selected. I'm making the wish list. It's not Christmas, but yeah.
And do you think there is this is currently being we're on the right path, or does it still need more time or more years?
This is a challenging question. Yes, it's on the right path. I mean, there are many teams trying to do that, but it's very long-term experiments. I mean, even for C60, if we take the example of C60, so this morning we were discussing about the timescale for telescope in between the idea and the launch, so 20 to 30 years. It's for C60, which can be considered as a molecule, but can be considered as a very small solid. It took about the same. It took about 20 to 25 years to develop the technique to have it measured in the gas phase by action spectroscopy. So I mean, you can't do this if you fund things for a project of 3 years. So definitely. So it's the same for if you really want to have isolated dust, it's the same kind of path you expect. I mean, it's tens or 20s years per individual to get something meaningful. So we will maybe discuss this in the round roundtable about all the questions you never dare to ask, is that you generally need to have projects on short and long term at the same time.
Jérôme, you wanted to ask something?
So I probably missed it, but where the PHs or AUV carriers are formed?
Where are they formed?
Yes.
I mean, if they are really large species, they are formed in the ejecta envelopes and then evolving in the diffuse medium. You cannot form large pHs, very large ones from the gas phase in the abundances of 5% of the carbon.
But the ones we are starting to detect in dark clouds,
yes,
are they formed by gas phase processes bottom up? Were they in heritage?
For the moment, the models are not able to form it by pure gas phase astrochemistry. I mean, forming coronen by pure gas phase models. I mean, you really have to tune all the parameters. But we're discussing two different things, because we're discussing something that is 10 to the 12, a column acid of 10 to the 12 per square centimeter, with respect to something that is 5% of the budget. So it's making maybe some of them can be done by top-down chemistry and at the interface at intermediate visual extinction. But for this, we need the information I was talking. We still do not know where it is exactly in the line of sight.
But I think there is a map of one of these pHs where you see extended emission in the dark cloud. So like telling you it's everywhere. You know?
No, but you mean the one detected in radio?
Yeah.
But it's you still need to know where it is in depth, not projected.
From the observation, you have the diffuse medium of external galaxy for the silicates. Do you have an idea if the depletion factor that you show in one of the first slide are consistent?
I don't have this information, and you probably have maybe people in the room. Frédéric would be better to answer to this question, but it's an interesting question. Can we find media where we can test this? And in the discussion, the previous discussion, there have been a lot of discussion about the nitrogen over oxygen ratio,
Exactly.
because there is a correlation that
because these are solar system and we're using that.
Yeah. But it would be nice to have the same thing for carbon over oxygen and relate this to silicates. Yes, I mean, but you can maybe complete.
Okay, we don't know.
What's a question there? No.
I was wondering, in an earlier lecture, we talked about the polarization effect of dust grains that are aligning with respect to a magnetic field. And I was wondering, how does this relate to the multitude of different dust species that you talked about?
I'm absolutely not the specialist to answer to this question. Even if we are looking at very detailed observations of very detailed regions, we sometimes still do not know what is the exact shape distribution. And we only have hints by models about what is compatible with the polarization in some cases, but we don't have a reverse engineering model. So we know, for example, that in many, we can talk about a recent, for example, drain model, where you have a kind of idea of the oblate ratio, where the ratio of the ellipsoid along different axes, which are compatible with the polarization you observe. But it's something that is not reverse engineered still yet. Still, you can put your intelligence into the system too. I mean, if you are using a size distribution, you have most of the size distribution used and the shape distribution used in many modelers use something that it's not spheres, it's not pure spheres. but it's not neither infinite long rods or infinite thin plates. So you have a kind of weighting schemes that are adopted by different people to try to modulate this. But it's a very tough question. And we need probably the information, as was discussed this morning, also of the polarization in the mid-infrared and in the far infrared to complete also all the information that have been recorded up to now from the visible and now going to the infrared to constrain this. But this is not my major, so.
Very good. One more letter.
Thank you for the lecture. On the carbonaceous matter, so you show that there is an aromatic part, a graphitase part with the pH and even certain way the fullerenes, and an amorphous part. Would it be possible to imagine structures that combine both, such as I would say soot analog, where there is an important graphitic part and in the amorphous carbon in the structures, even with defects on the surface and coating?
We expect that. I mean, and that was one of the goal of the mechanochemistry approach in some of the experiments. So the very short answer is yes, and you know it perfectly because I will ask you to do some calculation at some point about this kind of structures. So, but yes, it's you have mixed structures at some point. You needed also from the there are many aspects that were overlooked because we are going very fast and going back also on some of the structures. I mean, if you put an indent system, small systems, they won't be resilient to all these fields that you have at some point. So they will be destroyed. So you need a kind of protection. One way is to get quite inside class. Another one is to get in a larger system and have substructure that you preserve and that are more resilient just because you have a certain critical size that you can have some exchange with, still exchange with the gas phase and hydrogen exchange, but still conserve a part of the backbone. So.
All right, so one last question here.
So I had a question about the spinning dust component that is there. So there are, this is a observation from CMB maps where people find that in a few tens of gigahertz, there are dust grains which supposedly have a permanent dipole moment and they're spinning very rapidly. Is this something that is compatible with the observations in the lab? Where do these grains have a permanent dipole moment?
Observations in the lab, to my knowledge, there have not been a lot of experiments in the lab looking at this. It's more model-like, but this can be modeled quite. Well, I'm not a specialist of that, so but it's more on the model aspects.
All right.
It's very difficult to get an isolated grain spinning and measuring. I mean, it's from the experimental point of view, it's very difficult.
So any urgent question before lunch? No? So then let's thank Emmanuel.
Thank you.